Hi everyone. We're going to talk about the quantum model today. And we had left off talking about the Bohr model. And the thing to remember about the Bohr model is that it's incorrect and only works for hydrogen. So we need a better model. The one thing to take from the Bohr model, though, the big breakthrough was that these energy levels were quantized. And the quantum model grew out of all of the scientists kind of studying and trying to figure out different things at this time. So, like 100 years ago, I don't know exactly when it was. But what we want to do with this is just get a taste of it. And so, this is kind of a challenging topic for a Gen Chem class. It's a class that chemistry majors would take an entire semester class on, and it's really interesting, fascinating stuff, right? And there's all kinds of, this is where the science or reality is stranger than you can imagine, and the quantum mechanical world is where that really, I think there's some interesting results of it anyway. So what we want to do though is we just want to get a little bit of a taste of it to help us understand electronic orbitals and electron configurations and where they come from. So there's a couple of pieces of it that we'll discuss. And so we had talked about with electromagnetic radiation that it light behaves as both a particle and a wave. And those behaviors, what we observe physically, we can observe some behavior of electromagnetic radiation that we can use analogies of particles that we can see, like a baseball or a bullet or something like that, and also has some properties that make it look like a wave, like water waves and interference and diffraction, refraction, all of those things, light bending when it goes into a denser material like water. And so that's really interesting. And I had said, my understanding now of electromagnetic radiation is really that it behaves as neither. It's just something entirely different. There's an old Monty Python. That's way too old for even for your parents probably. But anyway, something entirely different. So the quantum model and quantum mechanical particles in the quantum mechanical world is really, we use these analogies of macroscopic things that we can observe, the classical physics, um, momentum, and all of that. And when we get down to really, really tiny particles, they don't behave that way. But because we understand the world just based on watching cause and effect that we can see in the macroscopic world, we use analogies to explain it and to study it, and that's where this stuff came from. But now it's basically, the way I understand it anyway, is quantum mechanical particles, small things like electrons and photons and protons, behave like they behave, and there's nothing like it that we see at our size scales. um, and they basically behave as the mathematical equations that describe their behavior tell us they behave, and that's what quantum mechanics is. So it's a lot of math, which we aren't obviously doing, um, but there's a couple of pieces that we're going to talk about before we get to quantum numbers. So the first thing is, just like electromagnetic radiation can exhibit properties of macroscopic particles and waves, if that statement makes a little more sense or more clear, um, we can also observe wave behavior of particles. So we don't think of it that way, but it is true. And in fact, electrons are small enough that their wave behavior is significant. And so just like a photon can have properties of a particle and a wave, electrons can do the same thing. They have the same kind of properties and behaviors. And so this was and in fact, there's a homework problem in the book. I think this book has it. I'll have to see if I can find it, where you can have a baseball or a basketball and talk about its wave behavior. And it does, everything behaves according to the quantum mechanical model. It's just that those particles are so big that it's irrelevant. It's not noticeable. All right, so the breakthrough then was this idea that, well, if light can act as a particle in a wave, maybe particles can act like waves as well, things like electrons. And so de Broglie, and again, we don't need to know the names of these people, but it's called the de Broglie equation, came up with an equation to describe this. So let's see if I can explain it a little bit. So we had our energy from before of a photon that's Planck's constant times the speed of light over the wavelength. But there's also a famous equation that I'm sure you've seen, E equals mc squared. And so you can take these two, set them equal to each other, and let's just plug it in, okay? So let's plug it in and solve for the wavelength. So let me see how we do this. So we've got hc over the wavelength, and then mc squared. So let's solve for the wavelength, okay? So we would get wavelength is equal to hc, and then we can plug in for the energy, the mc squared. Does that make sense? So I'm multiplying through by wavelength, and then I'm dividing through by the energy. But the energy is mc squared. So let's do that. Mc squared. And then, of course, we can cancel out one of the speeds of light, and we're left with this equation. Wavelength is equal to Planck's constant over mass times the speed of light. And then instead of just talking about the speed of light in there, we're going to now just call it the velocity, because this is going to apply to any particle. So m is the mass and v is the velocity. All right, so that's the idea, and we can then calculate the wavelength of anything. We can calculate the wavelength of an electron. We can take a 100-mile-per-hour baseball and take its mass and calculate its wavelength. We can calculate the wavelength of any object. And the thing that matters here is that if you do this calculation for a baseball, and I'll try and find the one in the book when I assign the homework, you'll notice then that that wavelength is so very tiny compared to the size of the baseball that it's unobservable, right? And that wave behavior, then you're not going to see that with a baseball. But for an electron, that wavelength is significant, okay, compared to the size, however you figure the size of an electron. And so that's why electrons can do all the same things that photons can do. Anyway, so just to sum up then, what this means is that the wave behavior is really important for really small particles. But then there's another aspect of it, because what if the velocity is really, really, really high? Okay, and so you can also have really, really fast particles and see those same effects. That's when the wave behavior would become important as well. All right, so that's one piece of it, right? One piece of quantum mechanics is that particles then can behave like waves, is what have wave-like behaviors as well. All right, now flip this over. One other thing, and then we'll get on to, I think the next thing is the actual quantum numbers. Oh no, there's two other pieces of it before we do the quantum numbers, which is on the handout. So this one is called the Heisenberg uncertainty principle. And what it says is that there's a fundamental limitation as to how well we can know something. And so I'm going to write out the statement of it. I should hit pause, but then the video keeps rolling anyway. But see, the idea is we cannot know or measure both the position and the momentum perfectly. There's a fundamental limitation in nature as to how well we can measure things for any object, any particle. Now, it's really important to understand that this doesn't mean that we haven't invented the technology yet to do it. It means that there's a fundamental limitation. No matter what, this is built into Mother Nature, that we can't know exactly at the same time the position and the momentum. Now, momentum means that's got the velocity in it. And no matter what we do, we can't invent better technology or anything else. This is built into nature, just like the constant pi. All right, so there's an equation then that usually expresses this, and that is the change in position. So x is going to be our position. So our uncertainty in that position that we know, that's what the delta means, the change in, times the uncertainty or the change in the momentum. Now, momentum is mass times velocity. This isn't a physics class, so don't freak out. We're just going to get a little flavor of this stuff. But momentum has velocity in it, right? And so we can't know momentum and position. So if you multiply perfectly, so if you multiply those two times each other, they are always greater than or equal to a constant. And that's where Planck's constant comes into play. And I think this is really kind of fascinating, because whenever you do, physics or chemistry and you see these pi, what's pi got to do with the price of tea and whatever, right? These constants pop up in Mother Nature all over the place. They're just built in there. And, because pi is the, right, circumference and diameter of a circle, you do the ratio, and that's where pi comes into play. But here it is popping up in this Heisenberg uncertainty principle. Anyway, so if you multiply your uncertainty in the position times the uncertainty in the momentum, that number is always bigger than Planck's constant over 4 pi. Can't be smaller than that. So that's the fundamental limitation built into nature. And so remember, just kind of going back a little bit, what we're interested in are these energy levels, and having an electron transition between two energy states, energy state 1, energy state 2, and popping up in there or popping back down. And so what this is saying in terms of spectroscopy, which is the emission of light, like we did in the demo the other day, it's saying that we can't know the energy of this exactly because, and this is another statement, so this is position and momentum, another statement of the Heisenberg uncertainty principle, because in order to know this energy exactly, the electron would have to stay there an infinitely long time for us to measure it. And so there's uncertainty in that as well. And there's a little bit, that means even though those atomic lines we saw were really, really sharp on those things, there is a fundamental limitation to that energy, right? To how well we can know it. All right, so I probably went into that a little too much. I'm going to flip the page, even though these pages are a lot bigger than my other notebook, but I want to make sure new topics on a new page. All right, so finally, so we've got a little piece of it. The first piece was that particles can have wave-like behavior, like electrons have wave-like behavior as well. And then the idea that we can't know the position and momentum exactly is built into quantum mechanics. And then, or the quantum nature of matter. So quantum just means, you know, it's countable, right? This is all discrete, not continuous. So quantum mechanics, this is a really hard topic, and I don't know how useful it is to present it in a Gen Chem class, but I try to be a responsible instructor. It's in the book, and we'll do the best we can. But so here's what we want to get out of it is the end result. So we just have to accept the math of it, right? We certainly can't do the math in a Gen Chem class. So there's an equation that the first time I saw it, I thought it didn't look like an equation at all to me. It's called the Schrodinger equation, and it looks kind of funky. And I'm going to put it on here. It's not anything we're going to use or know, but this is what it looks like. Okay, and this symbol is a psi, like, oh man, this is tough. Anyway, you know, the first time you see this equation, you're looking at, well, I'll just divide through by psi, right? And simplify it, and I'm done. But it's not really that kind of an equation. This isn't really the equation, okay? It's a function. And this is called, and you certainly don't need to know this, but I'm going to put it on there so we can at least talk about it. Psi is going to be something called the wave function. And what we're going to do, what chemists and physicists do is they come up with a mathematical function that they think will fit the behavior of the atom in the orbital. And they use that. And then this other thing, this H with a little hat on it, that's called the Hamiltonian operator. And again, you do not need to know that. But what that does is operates on the wave function, and when it does that, we can calculate the energy. So E is the energy. Again, just trying to get a little bit of flavor of this. All right. What comes out of this wave function is a probability function for the electron. And so it tells us what the probability is of finding an electron in a certain region of space, okay? And the wave function itself does not have any physical meaning. It's a mathematical equation that describes a probability function. And we don't, you know, I should probably not be saying as much about it as I am, right? But the one thing that we do have to know about it, because Gen Chem and that's what they want us to know, is that if we take that wave function, psi, and we square it, that's when we get that probability function for the electron. So I'm going to write this out carefully so I don't butcher it. It's the probability of finding an electron in a region of space. And so it does have a physical meaning, and it's that region of space around the nucleus, of course. It's a mathematical function that we then just square. So we need to know that. And then it's a probability function. So as you get farther and farther away from the nucleus, the probability goes down. And so all the chemists and physicists kind of have to agree what region of space are we going to call an orbital. And so what they all decided on, or most have decided on, the convention is that if we have a 90% probability, that's going to be our orbital. That's how we define an orbital. And this is where I do think it's a little bit unfortunate, right? The term orbital has the word orbit in it. And I just do want to stress that orbitals are not orbits. The electron isn't circling around the nucleus like the planet Earth is circling around the sun. That's not really the way to think about it. Rather, it's occupying the space around the nucleus according to the mathematical equations that we figure out in quantum mechanics. All right, I'm going to pause there and do a separate one on quantum numbers. Thanks.